Contents Introduction Ideal Properties Classification of Plasticizers. Mechanism of plasticization. Plasticizers used in soft gelatin capsules and tablets. Evaluation of plasticizers. Applications. Conclusion. References. Introduction. A plasticizer is a substance which, when added to a material, usually a plastic, makes it flexible, resilient and easier to handle. They are colorless, odorless liquids produced by a simple chemical reaction, whereby molecules of water are eliminated from petrochemical products. They are not just additives. They are major components that determine the physical properties of polymer products. Definition. A plasticizer or softener is a substance incorporated in a material, usually a plastic, to increase the flexibility, workability, dispensability. It may reduce the melt viscosity, lower temperature of second-order transition or lower the elastic modulus of the product. There are more than 300 different types of plasticizers available. The most commonly used plasticizers are ester-like phthalates, adipates and tremellitates. Ideal properties of plasticizers. It should be flexible, resilient and easier to handle. It should be non-volatile with high boiling point. It should not come out from materials to which it is added. Plasticizers used for internal purpose such as tablet coating, capsule shell manufacturing should be non-toxic. Lower the tensile strength and softening temperature of the polymeric materials to which it is added. It should reduce the brittleness, improve flow, flexibility, and increase toughness, shear strength, and impart resistance to the polymeric film coating. It should lower the glass transition temperature of the polymeric film coating. It should reduce the viscosity of materials to which it is added. It should impart permanent properties such as liability, shock resistance, hand drop. Classification of plasticizers. These are two types. Internal plasticizers. External plasticizers. Primary plasticizers. Secondary plasticizers. Internal plasticizers. A rigid polymer may be internally plasticized by chemically modifying the polymer or monomer so that flexibility polymer is increased. The process by which Tg of rigid polyvinyl chloride is lowered through copolymerization is called internal plasticization. External plasticizers. These are high-boiling liquids, non-volatile and having low vapor pressure. They must soluble in polymer and reduce the Tg of polymer below room temperature, rendering it softer and flexible. They act as lubricants between the polymer chains, facilitating slippage of chain under stress. Primary plasticizers. Also called as chemical plasticizers, when added to polymer, will cause the properties of elongation and softness of the polymer to be increased. Secondary plasticizers. Also called as plasticizing oils. They are not used alone, but when combined with primary plasticizers will enhance the plasticizing performance of the primary plasticizer. Types of plasticizers. Phthalates. Adipates. Citrates. Phosphate esters. Polymerics. Esters of glycol and polyhydric alcohols. Sabacate nadazolate esters. Secondary plasticizers. Tremellitates, phthalates. Both orthophthalic and terephthalic acids are used to react with alcohol to produce phthalate esters. Alcohol used in the range from methanol C1 up to C17. When added to vinyl, phthalate molecules are tightly bound up between the long vinyl molecules, making them slip and slide against each other without sacrificing strength. Advantages. Migration is less. Readily biodegradable. Does not cause any harm to body. D2-ethylhexylphthalate. Also known as deoctylphthalate. It is considered as the industry standard. It is phthalate ester with alcohol 2-ethylhexanol. Advantages. Low cost. Possesses reasonable plasticizing efficiency, fusion rate, viscosity. Disadvantages. It is toxic. B. Diazodecyl phthalate DIP and diazononyl phthalate DINP. These are prepared from oxoalcohols of carbon C9 and C10. These are used for heat-resistant electrical cards, leather for car interiors and PVC flooring in concentration of 25 to 50%. Adipates. Adipates are prepared from alcohols in the C8 to C10 range. They are having improved low-temperature performance and low viscosity. They are highly volatile, having high migration rate and are high-priced. Citrates, phosphates. These include triethyl citrate, acetyl triethyl citrate, tributyl citrate and acetyl tributyl citrate. Tributyl citrate is heat stable and does not discolor when processed in compound resins. These esters used in electrical coatings, food industry, hairsprays and inks. Phosphates. They show good compatibility with PVC. They are having good low-temperature performance, migration resistance and improved fire retardancy relative to phthalates, esters of glycols and polyhydric alcohols. Polymerics. These are produced by reacting a dibasic carboxylic acids with one or more glycols. These are manufactured in a wide range of viscosities. With increasing viscosity, handling become more difficult. The optimum viscosities of some acids are adipates 5600 CPS, glutarates 12,000 CPS. Esters of glycols and polyhydric alcohols. Polyhydric alcohols are propylene glycol, glycerol, polyethylene glycol and esters of glycols are glycerol triacetate, triethyl citrate. These are water-soluble and used in aqueous film coatings. Secondary plasticizers. They are also known as extenders. The majority of these plasticizers include chlorinated paraffins, which are hydrocarbons chlorinated to a level of 30–70%. The fire retardancy and viscosity increases with chlorine content. Other materials used are epoxidized soybean oil and epoxidized linseed oil. They act as lubricants to PVC due to their epoxy content. Sabacate and acylate esters. Tremellitates. Common esters in these family are tris-2-ethylhexyl tremellitate, L810Tm, an ester of mixed C8 and C10 linear alcohols. Advantages: low volatility, low migration rate. Sabacate and acylate esters. D2-ethylhexyl sabacate, DOS, and D2-ethylhexyl acylate, DOZ, are the most common members of this group, but diazodecyl sabacate, DIDS, is also used. They give superior low-temperature performance than adipates. Iron. Glass transition temperature Tg. The temperature at which the glassy polymer becomes rubbery on heating and rubbery polymer reverts to glassy on cooling is called the glass transition temperature. Polymer in rubbery state are very viscous liquids with relatively high freedom of rotation round the carbon-carbon bonds in the backbone within the constraint of tetrahedral bond angle. The temperature is high enough so that most bonds capable of overcoming potential energy barrier against rotation. This rotational freedom results in very flexible chains. Plasticizer triethyl citrate acetyl triethyl citrate tributyl citrate. Glass transition temperature of Udraget RS30D polymeric films. Plasticizer. 10% plasticizer. 20% plasticizer. Triethyl citrate. Acetyl triethyl citrate. Tributyl citrate. Acetyl tributyl citrate. Triacetin. Tg of unplasticized film is 55 degrees Celsius. 34.3, 37.0, 38.5, 38.2, 42.2, 12.8, 17.5, 20.5, 22.2, 27.4. Tg of Udraget RS30D degree Celsius. Mechanism of plasticization. Some involve detailed analysis of polarity, solubility and interaction parameters and the thermodynamics of polymer behavior, whilst others treat plasticization as a simple lubrication of chains of polymer, analogous to the lubrication of metal parts by oil. The following steps are involved in the incorporation of a plasticizer into a PVC product. 1. Plasticizer is mixed with PVC resin. 2. Plasticizer penetrates and swells the resin particles. Theories of plasticization are: 3. Polar groups in the PVC resin are freed from each other. 4. Plasticizer polar groups interact with the polar groups on the resin. The structure of the resin is re-established, with full retention of plasticizer. Theories of plasticization are: the lubricity theory, the gel theory, the free volume theory, gel theory, lubricity theory. A dry polymer, a resin without plasticizer, is rigid because friction exists between its chains, binding them into a network. When the polymer is heated in order to be plasticized, the binding is weakened and the smaller plasticizer molecules are able to slip in between the chains. When the polymer cools, the plasticizer molecules act as a lubricant between the chains, allowing them to slip. Gel theory. The plasticizer molecules break up the polymer-polymer interaction by getting in between the chains and obscuring these interaction sites from the polymer molecules. The free volume theory. The free volume of a polymer can be described as the empty internal space available for the movement of the polymer chains. The free volume of a polymer greatly increases when it reaches the glass transition temperature. At the glass transition temperature, the molecular motion begins to occur, which corresponds to an increase in the free volume of the polymer. These plasticizer molecules are having low glass transition temperature than the polymer, so that Tg of the resulting mixture will be lower. Plasticizers used in capsule manufacture. The most common plasticizers used in manufacturing of hard and soft gelatin capsules: polyvinyl alcohols, sorbitol and propylene glycols. The amount and choice of the plasticizer help to determine the hardness of the final product, and may also affect the dissolution or disintegration of the soft gel, as well as its physical and chemical stability. The ratio of dry plasticizers to dry gelatin determines the hardness of the shell and can vary from 0.3 to 1.0, for a very hard shell, 1.0 to 1.8 for a very soft shell. Up to 5% sugar may be included to give chewable quality to shell. Typical shell hardness ratios and their uses. Ratio of dry glycerin/dry gelatin. Usage: hard 0.41. Oral, oil-based or shell softening products and those destined primarily for hot, humid areas. Medium 0.61. Oral tube, vaginal oil-based, water-miscible-based or shell hardening products and those destined primary. Soft 0.81. Tube, vaginal, water-miscible-based or shells hardening products and those destined primary for cold, dry areas. Plasticizers in transdermal drug delivery patches. Acrylic acid matrices with plasticizers have been used to make drug polymer matrix films for transdermal delivery systems. Some of the polymers that have been reported are Udraget RLPM, Udraget RSPM, Udraget S100. Ethyl cellulose and PVP matrix films with 30% dibutyl phthalate as a plasticizer have been fabricated to deliver diltiazem hydrochloride and indomethacin. The addition of hydrophilic components such as PVP to an insoluble film former such as ethyl cellulose tends to enhance its release rate constants. Plasticizers in film coating. The commonly used plasticizers can be categorized into three groups. 1. Polyols. A. Glycerol, glycerin. B. Propylene glycol. SC polyethylene glycols PEG, generally the 200 to 6000 grades. 2. Organic esters. A. Phthalate esters, diethyl, dibutyl. B. Dibutyl subacet. C. Citrate esters, triethyl, acetyl triethyl, acetyl tributyl. D. Triacetin. 3. Oils/glycerides. A. Castor oil. B. Acetylated monoglycerides. C. Fractionated coconut oil. Plasticizers used in controlled release drugs such as dibutyl sabacate diethyl phthalate, triacetin, triethyl citrate, acetylated monoglyceride. Plasticizer acts as a film-forming aid by reducing the glass transition temperature of the polymer, thereby promoting the coalescence of the latex particle. The degree of plasticization of a polymer is dependent on the amount of plasticizer added. Interactions between the polymer and plasticizer. Effect of plasticizers on the mechanical properties of the film. Common methods used to evaluate mechanical properties of polymeric films include microindenter probe analysis, and shear tests, and stress relaxation. The stress strain test is probably one of the most popular and widely used technique to determine the mechanical properties of polymeric materials. Stress strain testing generally consists of applying an axial load to an isolated free film and measuring the load and deformation simultaneously. The stress strain test will provide a generalized curve from which several useful properties can be determined. The basic requirements to be met by a plasticizer are permanence and compatibility. Compatibility demands that the plasticizer must be miscible with the polymer and exhibit similar intermolecular forces to those present within the polymer. Permanence is an attribute to be taken into consideration as loss of plasticizer. It leads to the cracking of the coating under inappropriate storage. Permanence is obviously related to plasticizer volatility. However, a change to a more non-volatile plasticizer by changing to a higher molecular weight plasticizer is not always an advantageous move. Water vapor transmission cell. Effect of plasticizers on permeability of film coatings. Water vapor transmission cell. These water vapor transmission cells rely on a vapor pressure gradient to achieve a linear weight gain. From the daily weight gains, the water vapor permeability constant can be calculated using equation, where perm is the moisture permeability constant, W is the amount of moisture transmitted per unit time, L is the thickness of the film, A is the area of the film exposed, and dP is the vapor pressure gradient. Water vapors have been shown to permeate more rapidly through films containing hydrophilic plasticizers, whereas the inclusion of a hydrophobic plasticizer in the coating has been found to exert no significant effects on water vapor permeability. Evaluation of film properties. The free films were cut into strips of 70 mm x 10 mm for evaluation of mechanical properties, or circular pieces with diameter of 7.46 cm for determination of water vapor permeability. Film thickness was determined by measuring the thickness at 5 scattered points on the film, using a digital micrometer, Mitutoyo, Japan, and the values averaged. Only film samples with mean thickness within the range of 180 to 220 mm and thickness value variation less than 10% in each film were used for the above tests. Film samples used for mechanical testing, assay of plasticizer and moisture content and determination of percent weight change were stored in controlled environment chambers of 30 degrees Celsius and 50 or 75% RH. Samples were equilibrated at ambient room condition of 22 + 2 degrees Celsius and 55 + 2% RH for 1 hour prior to testing. This is to minimize any variations in result due to room condition. Mechanical properties. The mechanical properties of the films were evaluated using a tensile testing instrument, Easy Test 100N, Shimadzu, Japan, mounted with a 100N capacity load cell. For mechanical properties, namely tensile strength, percent elongation at break, elastic modulus and worker failure were computed from the load, strain profile, and film dimensions as shown below. T equals Lmax/I, 1. E equals pound/Li, 2. M equals DL/DM/I, 3. Omega equals Oc X delta/I, 4. Plasticizer content. The amount of plasticizer in the aquacoat film was determined using gas chromatography, Model 5890 Series 2 Hewlett-Packard, with a split/splitless inlet, a 23.5 meters by 0.32 millimeters fused silica polyethylene glycol capillary column, HP FAPEX-linked polyethylene glycol, and a flame ionization detector. About 200 milligrams of film sample were accurately weighed and dissolved in methanol. An internal standard of 1 milliliter was then added to the mixture. Triethyl citrate, TEC, 5, was employed as the internal standard for GTA, while glycerin triacetate, GTA, 10, solution was the internal standard for the rest of the plasticizers. Using methanol, the mixture was made up to a final volume of 20 milliliters for dibutyl phthalate, DBP, and 10 milliliters for the rest. Nitrogen was used as the carrier gas at a flow rate of 28.5 milliliters per minute, with injector temperature at 240 degrees Celsius and detector temperature at 270 degrees Celsius. For the assay of DEP, TEC, ATEC and GTA, the column temperature was increased from 150 degrees Celsius to 230 degrees Celsius at a rate of 10 degrees Celsius per minute and held at 230 degrees Celsius for 3 minutes. For the assay of DBP and acetyl triethyl citrate, ATEC, the column was heated up from 150 degrees Celsius to 240 degrees Celsius at a rate of 10 degrees Celsius per minute and held at 240 degrees Celsius for 5 minutes. Applications. The plasticized PVC is used for life-saving medical devices such as medical tubing and blood bags, TO footwear, electrical cables, packaging, stationery, and toys. Phthalates are used in other non-PVC applications such as paints, rubber products, adhesives and some cosmetics. The butyl benzyl phthalate plasticized polymeric material has consumer and industrial uses such as flooring, sealants and coatings. Pharmaceutical applications. Used in functional and non-functional coating of solid dosage forms, including tablets, beads and granules, such as film coating, enteric coating, osmotic tablet coatings etc. to impart flexibility to the different types of coating materials. In the production of soft gelatin capsules. In the manufacture of life-saving medical devices such as for administration, dialysis, cardiopulmonary bypass, CPB, procedures, bags used to store and transport, enteral nutrition formulae, total parenteral nutrition formulae, tubings used in enteral nutrition, nasogastric tubes, nasojejunal tubes, also used in manufacturing of transdermal patches. Conclusion. Plasticizers are necessary for almost all polymers that are currently used for film coating of tablets and beads. Plasticizers reduce the brittleness, improves flow, impart flexibility, and increase flexibility, and increase toughness, strength, tear resistance of polymers. Although there are many plasticizers used in chemical industry, only a few plasticizers have been approved for pharmaceutical applications due to environmental and human health concerns attributed to plasticizers' toxicity. References. 1. D.F. and Howick, C.J., Plasticizers, Encyclopedia of Chemical Technology, 419, 258-290 1996. 2. Porter's Coating of Pharmaceutical Dosage Forms, Remington's Book of Science, 1, 894-902. 3. Encyclopedia of Pharmaceutical Technology by James Swarbrick, 1734, Volume 3. 4. Secolaro, P., Rowe, R., C., and White, E., F., Int. J. Farm, 31, 55, 1986. 5. Entwistle, C., A. and Rowe, R., C., J. Farm, Pharmacal, 31, 269 1979. 6. Porter, S., C., Farm, Tech, 43, 66, 1980. 7. Alton, M. E., Twitchell, A. M., and Hogan, J. E., Proceedings of AGPI Conference, Paris, 1986. 8. Crawford, R., R. and Esmerian, O. K., J. Farm. Set. 62, 312, 1971. 9. Entwistle, C. A. and Rowe, R. C. J. Farm, Pharmacology. 31, 269 1979. 10. Scultity, P.F. and Sims, S. Drug Dev. Indiana Farm. 13, 2209-2219, 1987. 11. Alton, M.E., Abdul Razak, M.H. and Hogan, J.E. Drug Dev. Indiana Farm. 7649-648, 1981.